Hello there, and welcome back to Sleeping with Science Stories, where every night we leave the weight of the day behind and drift together into a different kind of journey. One that needs no ticket, no luggage, just you and a mind willing to open up. If these journeys bring you a little peace, go ahead and hit like and subscribe so we can keep exploring together, night after night. Tonight, we're going far. Further than the night sky outside your window. Further than the moon. Further than the sun. Further than any star your naked eye has ever caught. We're going to touch the oldest light that has ever existed, listen to stars sing, and stand before mysteries that even science is still quietly whispering about. So, close your eyes and let the universe tell you its story. Have you ever looked up at the night sky and wondered, how old is that light really? The light coming from those stars? Here's something strange to sit with. When you look at a star, you're not seeing it as it is right now. You're seeing the past. The light from our nearest stellar neighbor, Proxima Centauri, takes over 4 years just to reach your eyes, which means tonight, when you look at it, you're actually seeing a moment that already happened 4 years ago, and that's just the neighbor next door. For galaxies further out, the light you're seeing may have started its journey millions, even billions of years ago. When that light left its source, Earth didn't exist yet. Dinosaurs hadn't even crossed anyone's mind. Our sun hadn't been born. The universe, as best as we currently understand it, is about 13.8 billion years old. Try to feel that number for a second. 13 billion, 800 million years. If you squeezed the entire history of the universe into a single calendar year, Earth wouldn't show up until mid-September. The dinosaurs would go extinct on December 30th. In all of human history, every step our ancestors took across the African savanna, every war, every love story, every invention, every poem would happen in the last few seconds of December 31st. In a very real sense, we just got here. But is 13.8 billion years really the final answer? In recent years, the James Webb Space Telescope, JWST, has made scientists stop and exchange some seriously puzzled looks more than once. JWST was built to peer back to nearly the very beginning of the universe, and it did exactly that. But along the way, it found something no one was fully prepared for: galaxies that looked way too grown up, too large, too well-formed for their age. These galaxies existed when the universe was only a few hundred million years old, but they had the size and structure of galaxies billions of years in the making. It's like running into a 6-month-old baby who's sitting in an armchair reading philosophy. Now, this doesn't necessarily mean the universe is older than 13.8 billion years, but it does mean we might be missing something. A puzzle piece that doesn't quite fit the current picture. Maybe those first galaxies formed faster than we ever thought. Maybe dark matter plays a different role than our current models suggest. Or maybe, and this is the kind of possibility that keeps theoretical physicists up at night, maybe something happened before the Big Bang that we haven't been able to reach yet. Science doesn't shy away from questions like that. If anything, questions like that are exactly why science exists. There is one very special kind of light, the oldest light humanity has ever been able to observe. Not from a star, not from a galaxy, but from the actual dawn of the universe itself. About 380,000 years after the Big Bang, the universe had cooled just enough for electrons and protons to come together and form the very first atoms. Before that moment, the universe was so dense and so hot that light couldn't move freely. It kept getting absorbed and re-emitted, like a voice trying to carry across a room packed wall to wall with people. But when those atoms formed, the universe suddenly became transparent. Light was free, and it started to run. That light is still running today. We call it the cosmic microwave background, the CMB. You can't see it with the naked eye, but it blankets the entire sky in every direction, like a thin, fossilized glow wrapped around us. Its temperature has dropped to about minus 270 degrees Celsius, just barely under 3 degrees above absolute zero. That's the lingering warmth of a fire that burned nearly 14 billion years ago. When scientists first discovered the CMB back in 1965, completely by accident, while two Bell Labs engineers were trying to figure out why their antenna kept picking up static, they had no idea what they were hearing. It wasn't until later that they realized this was the echo of the Big Bang, the reverberation of the moment everything began. And here's what makes it even more beautiful. The CMB isn't perfectly uniform. If you measure it carefully enough, you'll find these incredibly tiny ripples in its temperature. Spots that are just a hair warmer. Spots that are just a hair cooler. Those ripples are the seeds of everything. From those tiny fluctuations in the CMB, gravity slowly pulled matter together over time, building clouds of gas, then the first stars, then galaxies, then galaxy clusters, then the entire vast web of structure we see in the universe today. All of it traced back to tiny wrinkles in the echo of an explosion nearly 14 billion years ago. Let's come back to JWST for a moment. This telescope operates in infrared, a kind of light our eyes can't see, but one that's perfect for cutting through thick clouds of cosmic dust and picking up objects at extreme distances. And since light takes time to travel, the further out you look, the further back in time you're seeing. In the most literal sense possible, JWST is a time machine. One of the most distant galaxies JWST has observed goes by the rather dry name JADES GS Z14-0. The light from this galaxy began its journey when the universe was only about 290 million years old, roughly 2% of its current age. Think about that. You're looking at light from a galaxy that set out on its travels when the universe was barely a newborn. It's been crossing space for 13.5 billion years, covering distances too vast to wrap your head around. And then it finally lands on the mirror of a telescope humanity built just a few years ago. There's something both overwhelming and strangely moving about that. And that galaxy, at that distance, seen when it was still so young, already held hundreds of millions of stars, forming, lighting up, starting their stories we'll never see the ending of, because the light from the rest of those stories is still on its way to us. The universe isn't just space. The universe is time, laid out right before your eyes. In science, not every question has an answer. And sometimes, the unanswered questions are the most beautiful ones of all. How old is the universe, really? We think 13.8 billion years. But if something was happening before the Big Bang, if the Big Bang was just one event in a longer chain we haven't seen yet, then that number might only be one chapter in a much longer book. The oldest light we can see is the CMB, from 380,000 years after the Big Bang. But what about before that? The universe back then was opaque. Light was trapped. We can't look back any further using light. But maybe using gravitational waves, primordial neutrinos, tools we haven't even invented yet. Maybe someday we'll be able to hear the echo of moments even older than that. And when that happens, the picture of the beginning will change all over again. That's the most beautiful thing about science. It never claims to be finished. It's always on its way somewhere. Try to imagine this. You're standing alone in the middle of a vast desert at midnight. No streetlights, no traffic, nothing at all. Just the sky and you. You tilt your head back and look up. Thousands of stars. They shimmer. They glimmer. They look almost close enough to touch. But here's something most people never stop to think about in that moment. Not a single one of those stars is actually present with you right now. Everything you're seeing is the past. Light has a speed, and that speed, the fastest anything in the universe can travel, still takes time to get from one place to another. Light from the sun takes 8 minutes to reach Earth, which means the sun you see every morning is actually the sun as it was 8 minutes ago. If the sun were to vanish this very second, you wouldn't know for another 8 minutes. And for stars further out, the light you're seeing tonight may have started its journey hundreds, thousands, even millions of years ago. Some of those stars may already be gone. They exploded, collapsed, disappeared entirely. But their final light is still out there, still racing through the dark. And tonight, it lands in your eyes. You are seeing the light of dead stars. And somehow, that's not sad at all. It's actually kind of beautiful. Our universe, by our best scientific understanding, is about 13.8 billion years old. That number comes from multiple independent lines of evidence. The rate at which the universe is expanding, the ages of the oldest known stars, and the cosmic microwave background radiation. For decades, measurements from completely different directions kept converging on roughly the same answer. That gave scientists a lot of confidence. But then, a small problem came up, and it's been getting harder to ignore. The problem goes by the name Hubble tension. The Hubble constant is the number that describes how fast the universe is expanding. When you measure it by looking back at the cosmic microwave background, essentially looking at the ancient universe, you get one number. When you measure it using nearby stars, looking at the universe as it is today, you get a different number. And those two numbers don't agree. The gap between them has now grown beyond what normal measurement error can explain. What could that mean? There are a few possibilities. Maybe there's a flaw somewhere in the measurements. Maybe our current model of cosmology is missing an ingredient. Or, and this is the boldest possibility, maybe the universe doesn't quite work the way we think it does. And if that's the case, that 13.8 billion year figure might just be an approximation. Our best answer so far, but not necessarily the final one. Have we been missing something? That question is still hanging in the air of modern science, without a satisfying answer. But regardless of where the debate over the universe's age lands, there's one thing we're nearly certain of, and it's one of the most beautiful discoveries humanity has ever made. That's the cosmic microwave background, the CMB. To understand what the CMB actually is, you have to rewind to the very first moments after the Big Bang. The universe back then looked nothing like anything we can picture. No stars, no planets, no atoms. Just an incredibly hot, dense sea of plasma, a chaotic soup of fundamental particles constantly smashing into each other. In that environment, light couldn't get anywhere. Every time a photon, a particle of light, tried to travel, it was immediately absorbed and re-emitted by the surrounding particles. The universe at that point, if you could somehow stand inside it, would have looked like an impenetrable wall of thick fog. That went on for about 380,000 years. And then something happened. The universe cooled down. And when the temperature dropped low enough, around 3,000 degrees Celsius, electrons began joining with protons to form the very first hydrogen atoms. Physicists call this moment recombination, and it changed everything. The instant those atoms formed, the universe suddenly became transparent. Light was no longer blocked. And in one cosmic moment, all the light that had been trapped inside that plasma fog was released at once. It started running. And it's still running right now. That's the CMB. That light has been traveling for nearly 13.8 billion light years. And over that entire journey, the expanding universe has been stretching it out, cooling it down, shifting it from visible light into microwave radiation, invisible to the naked eye. But it's still there, blanketing the entire sky in every direction. Its temperature has dropped to about 2.7 Kelvin, roughly minus 270 degrees Celsius, just a hair above absolute zero. That's the leftover warmth of the universe's dawn. The echo of a fire that burned nearly 14 billion years ago. And here's what makes it even more fascinating. The CMB isn't perfectly smooth and uniform. If you measure it with extreme precision, you'll find tiny ripples in its temperature. Regions that are 100,000th of a degree warmer. Regions that are 100,000th of a degree cooler. Those ripples seem almost too small to matter, but they are the seeds of everything. From those tiny irregularities, gravity gradually pulled matter together, building clouds of gas, then stars, then galaxies, then galaxy clusters, then the entire enormous cosmic web we observe today. Every structure in the universe, every star, every planet, every galaxy, and you can be traced all the way back to tiny ripples in a hot fog from nearly 14 billion years ago. In 2022, humanity put one of the greatest scientific instruments ever built into operation, the James Webb Space Telescope, or JWST. Unlike the Hubble, which works primarily in visible light, JWST observes in infrared, a kind of light invisible to the human eye, but absolutely essential for seeing into the most distant corners of the universe. Here's why. When light from very distant galaxies travels toward us, the expanding universe stretches that light out along the way, shifting it toward longer wavelengths, toward the infrared. This is called redshift, and JWST was designed specifically to catch those infrared signals. In its early years of operation, JWST kept sending back images that made astronomers stare at their screens and do a double take, genuinely unsure of what they were looking at. One of the most distant galaxies JWST has observed, with the scientific designation JADES GS Z14-0, existed when the universe was only about 290 million years old. The light from that galaxy started its journey 13.5 billion years ago. When that light left its source, our sun didn't exist. Earth didn't exist. Most of the stars in our own Milky Way hadn't even been born yet. And that light, after a 13.5 billion year journey, landed on JWST's mirror, was captured, was analyzed, was seen by human eyes. But what truly shook everyone wasn't just the distance. It was what that galaxy actually looked like. According to the standard model of cosmology, galaxies at that age, just a few 100 million years after the Big Bang, should have been small, messy, in the middle of chaotic early formation. But what JWST kept finding were galaxies that looked strangely mature, bigger than expected, more structured than expected, churning out new stars far faster than anyone predicted. It's like cracking open a family photo album and finding a picture of a 6-month-old baby. Except in the photo, the kid is standing upright, wearing a suit, and reading a thick philosophy textbook. Something doesn't add up. And in science, when something doesn't add up, it's usually a sign that a new discovery is waiting just around the corner. Maybe the first galaxies formed faster than we ever imagined. Maybe dark matter played a bigger role in driving early star formation than we thought. Maybe the standard cosmological model needs to be revised, updated, or in some parts completely rewritten. We don't know yet. And that not knowing, rather than being frightening, is exactly what keeps science alive. There's a small, beautiful paradox hiding inside all of this. We tend to think that seeing further means knowing more about the universe as it is now. But in reality, the further out you look, the further back in time you're seeing. JWST peers so far out that it's literally observing the universe when it was still in its infancy. The galaxies it photographs, we have no idea what they look like today. They may have grown up, merged with other galaxies, changed their shapes entirely, or they may have been swallowed by something larger billions of years ago. The light we're receiving from them is a letter sent 13.5 billion years ago that only just arrived today. And that letter, ancient beyond comprehension, still contains information we haven't fully decoded. The universe has written many letters like that, and we, with ever more powerful telescopes, ever more sophisticated algorithms, and a curiosity that never quite runs out, are still sitting here reading them, line by line, photon by photon. We've been talking about light, those ancient letters the universe has been sending us across billions of years. But not everything in the universe bothers to write. Some objects exist in complete silence, drifting through the dark, not giving off nearly enough light for us to easily see them. And some worlds are so different from our own, our warm, green, life-filled blue planet, that they look like the strangest dreams a human imagination could ever conjure. Let's start with the wanderers. Rogue planets, worlds without a home. In our solar system, every planet has a star to orbit. Earth goes around the sun. Jupiter goes around the sun. Even Pluto, despite its famous demotion to dwarf planet, faithfully follows its orbit around the sun. That's the image we grew up with. Planets belong to stars. That's just the natural order of things. But the universe doesn't care about the order we imagine. Out there, in the darkness between the stars, there are billions of planets that don't belong to anyone. They drift alone through space. Cold, dark, no sunlight to warm them, no fixed orbit to follow. We call them rogue planets, or sometimes, more poetically, lonely planets. How does a planet end up that alone? A few different ways. Some were flung out of their solar systems during violent early phases, when giant planets like Jupiter shifted their orbits and set off massive gravitational ripple effects, launching smaller planets outward like marbles flicked off a table. Others may have formed directly in interstellar space, not from a disk of material around a star, but straight from collapsing clouds of gas and dust, the same way stars form, just without enough mass to actually ignite. The sheer number of them is enough to stop you cold. Current estimates suggest that in our Milky Way alone, rogue planets may actually outnumber stars. Some studies put the figure in the trillions. Trillions of homeless planets, quietly drifting through the dark of the galaxy. And here's where the story gets really interesting. Some rogue planets may not be completely dead and frozen. If a planet is large enough, its core might still be holding on to heat left over from its formation. And with enough atmospheric pressure, liquid water could theoretically exist, not thanks to any sun, but from the warmth deep inside the planet itself. Kind of like the hydrothermal vents at the bottom of Earth's oceans, where life manages to thrive without a single ray of sunlight. Maybe, just maybe, somewhere out there in the cosmic dark, there's a lonely planet quietly warming a hidden ocean. And in that ocean, something is swimming. We don't know. But the universe is big enough that all kinds of possibilities get to exist. If rogue planets are the lonely wanderers, then diamond planets are the most extravagant worlds imagination can reach. And reality turns out to be even stranger than anything you dream up. Think about diamonds. On Earth, they form when carbon is subjected to extreme heat and pressure deep in the mantle, a process that takes billions of years and produces stones so rare that humans have been assigning them meaning and value for millennia. But in the universe, there are places where diamond isn't a rarity. It's a building material. The planet 55 Cancri E, a super-Earth about 41 light-years away, was once proposed by scientists to potentially have a mantle and crust made largely of carbon in the form of diamond and graphite. The immense pressure and temperature inside that planet, combined with its carbon-rich composition, could create the perfect conditions for diamond formation on a planetary scale. But the real showstopper is the white dwarf star BPM 37093, affectionately nicknamed Lucy by astronomers, after the famous Beatles song. This star, which is actually the remnant core of a dead star, is believed to have a carbon core that has crystallized entirely into diamond. The size of this diamond? An estimated diameter of about 4,000 kilometers. Its mass? Roughly 10 billion trillion carats. Let that one sink in for a second. 10 billion trillion carats. A diamond larger than Earth, floating in space about 50 light-years away. In a way, the universe is remarkably generous with the things we consider precious. It just keeps them somewhere we can't get to yet. If diamond planets leave you breathless with their extravagance, neutron stars will leave you breathless for an entirely different reason. For just how extreme matter can actually get. Neutron stars are born from the deaths of massive stars. When a star roughly 8 to 20 times the mass of our Sun reaches the end of its life, it collapses in a cataclysmic supernova explosion. But its core, rather than disappearing, gets crushed by gravity so intensely that electrons and protons are forced into each other, merging into neutrons. What's left is an object almost absurdly small, roughly 20 kilometers across, yet containing more mass than the entire Sun. The density of neutron star matter is beyond anything our intuition can handle. 1 teaspoon of neutron star material, just one small spoonful, would weigh around 1 billion tons. That's heavier than the entire Himalayan mountain range combined. And if you took a single raindrop, a tiny drop falling on a night just like tonight, and made it out of neutron star matter, that drop would weigh more than Mount Everest. 1 raindrop. Heavier than the tallest mountain in the world. The material inside a neutron star exists in states that modern physics still can't fully describe. The outermost layer is probably a hard crust of tightly packed atomic nuclei. Deeper in, neutrons begin to flow like a superfluid. And at the very center, where pressure hits its absolute extreme, there may be forms of matter we don't even have names for yet. Possibly quark matter, where neutrons dissolve and quarks exist freely in ways we've never seen. Neutron stars also come in a special variety called pulsars, neutron stars that spin incredibly fast and fire off powerful beams of radiation from both poles. When those beams sweep past Earth, we pick up pulses of signal as regular as clockwork, sometimes hundreds of times per second. So precise that astronomers once used pulsars as cosmic reference clocks. And then there's an even more extreme version called a magnetar. Its magnetic field is so powerful that if a magnetar were positioned on the exact opposite side of the Earth from you, its field would still be strong enough to wipe the data off your credit card. Get any closer, and wiped credit cards would be the least of anyone's problems. For centuries, musicians and philosophers dreamed of something called the music of the spheres, the idea that the movements of celestial bodies produced some kind of harmonious cosmic song. It was poetry, but it turns out the universe went ahead and made that poetry real. Deep inside every star, enormous pressure waves are constantly moving, compressing and expanding, compressing and expanding. These oscillations are completely silent to human ears. Space is a vacuum, and sound can't travel through it. But they're real, and they follow the exact same physical laws as a musical instrument vibrating to produce sound. A violin doesn't vibrate at just one frequency. It vibrates at a fundamental frequency and a whole series of harmonics, and that combination creates its distinctive tone. Stars work the same way. Every star has its own set of oscillation frequencies shaped by its size, mass, chemical composition, and age. The field of science that studies this is called helioseismology when applied to the Sun, and astroseismology when applied to other stars. By measuring the incredibly subtle flickering in a star's brightness, astronomers can essentially hear the frequencies that star is vibrating at, and from that, figure out what's going on deep inside it. It's a bit like a doctor using ultrasound to see inside the human body without ever picking up a scalpel. Our Sun is oscillating at millions of different frequencies simultaneously. If you converted those oscillations into sound and sped them up enough for human ears to catch, the sun would sound like an enormous pipe organ, complex, layered, continuous. A piece of music that's been playing without a single pause for 4.6 billion years. And every star has its own song. Older stars oscillate more slowly, with deeper tones. Younger, hotter stars oscillate faster, with higher frequencies. The Kepler Space Telescope, and later TESS, spent months and years listening to thousands of stars, picking up the tiny fluctuations in their light. And from that data, scientists have been able to build detailed portraits of those stars' internal structures without ever going near them. It turns out the universe isn't silent. It's just singing in a language human ears weren't built to hear. But science, with patience and ever more refined instruments, is slowly learning how to listen. A universe stranger than any dream. Planets wandering through space with no star to call home. Worlds literally built from diamond. Dead stars that have compressed matter so densely that a single drop of it would weigh enough to crush a mountain. And stars quietly singing. A soundless music ringing out across billions of years in the dark of the universe. No dream has ever been this strange. And this is only a tiny fraction of what the universe actually contains. Out there, in the vastness that light takes billions of years to cross, there are almost certainly things that even the richest human imagination hasn't come up with yet. Have you ever watched a candle slowly go out? The flame shrinks, the light fades, a thin thread of smoke rises, and then everything falls into darkness. You might think that's the end, but the wax is still there. The wick is still there. And with a single match, the flame comes back, as if it was never gone. The universe, according to some physicists, may work in a way not entirely unlike that candle. No real ending. Just pauses between flames. The universe is expanding and speeding up. To understand the story of cosmic cycles, we first need to grasp something fundamental. The universe is not standing still. It's expanding. And not just expanding, it's expanding faster and faster. In 1929, the astronomer Edwin Hubble observed that almost all galaxies were moving away from us. And the farther away a galaxy was, the faster it was receding. This was the first direct evidence that the universe was expanding. And if the universe is expanding, then running the clock backward, everything would have been closer together, hotter, denser, all the way back to a single starting point we call the Big Bang. But the story didn't stop there. In 1998, two independent research teams, who would later share the Nobel Prize in Physics, discovered something completely unexpected. The universe wasn't just expanding, it was expanding faster over time. That meant something. Some force we can't see, can't directly measure, and don't understand, was pushing everything apart. We call it dark energy. Dark energy makes up roughly 68% of the entire universe. And we know almost nothing about it beyond the fact that it exists and that it's causing the universe to spread apart at an accelerating rate. If that trend continues indefinitely, the universe will eventually expand so much that every galaxy, every star, and ultimately every atom will be pulled so far apart that nothing can ever interact with anything else again. That's one of the proposed end states that science calls the Big Rip. But that's just one possibility. There's another school of thought, one that many theoretical physicists have pursued with a lot of genuine excitement, that says the universe doesn't travel in a straight line from Big Bang to end. It travels in a circle, or more precisely, a spiral. This idea is called the Big Bounce. The core concept goes like this: rather than the Big Bang being an absolute beginning, a moment when everything suddenly came from nothing, the Big Bang was actually the result of a previous universe collapsing. Picture it this way. A universe exists. It expands for trillions upon trillions of years. Then, for some reason, maybe dark energy weakens. Maybe gravity finally wins. The expansion stops and reverses. The universe starts contracting. Slowly at first, then faster still. Everything rushing toward a single point, heating up to unimaginable temperatures, growing so dense that ordinary physics breaks down completely. But instead of collapsing to nothing, instead of ending, something happens at the quantum level. Matter and energy, compressed to their absolute limit, bounce back like a rubber ball thrown hard against the floor. And from that bounce, a new universe erupts. A new Big Bang, a new journey begins. Under this theory, our Big Bang wasn't the first event. It was just one beat in an endless sequence of beats. Universe contracts, bounces, expands, contracts, bounces, expands, repeating since before the word before had any meaning, and continuing long after there's anyone left to use the word after. No beginning, no end, just cosmic seasons, cycling one into the next, without a starting point and without a finish line. A bolder variation comes from Roger Penrose, the British mathematician and physicist who shared the 2020 Nobel Prize in Physics for his work on black hole theory. He's proposed a model called conformal cyclic cosmology, or CCC. Penrose's idea is subtle and strange in its own way. He argues that in the final stage of a universe, when all massive particles have long since disappeared, when all that's left are massless particles like photons drifting through an unimaginably vast and empty space, that universe actually becomes mathematically indistinguishable from a brand new universe just being born from a Big Bang. Why? Because both states, an almost infinitely diluted universe at its end, and an almost infinitely dense universe at its beginning, can be described using the same mathematical structure, as long as you ignore scale. Put simply, for massless particles, there's no such thing as big or small, only direction and speed. And in that mathematical language, the end of one universe is the beginning of the next. Death and birth, stitched together by an invisible mathematical thread. Penrose has even suggested that faint traces from a previous universe might be carried through into the next one, incredibly subtle ripples in the CMB radiation we talked about earlier. Some research groups have actually gone looking for those traces and claim to find signals, though the scientific community is still actively debating what they mean. But the idea itself is beautiful enough to just sit with. Maybe the universe before ours left a few faint brush strokes on the canvas of our universe, like a painter's signature hidden on the back of a painting. But before we get to any next cycle, our own universe still has an extraordinarily long road ahead of it, and that road according to most current models, leads somewhere called heat death, or sometimes the big freeze. Let me walk you through the stages of that distant future, not to cause any worry, but just to take in the sheer scale of time. Right now, we're living in what scientists call the stelliferous era, the age of stars. Stars are forming, burning bright, warming the planets around them. This era began about 100 million years after the Big Bang and will go on for roughly another 100 trillion years. Compared to that, the entire history of the universe so far, 13.8 billion years, is barely the opening paragraph. But eventually, stars will run out of fuel. One by one, they'll go dark. Massive stars will explode as supernovae, leaving behind neutron stars or black holes. Smaller stars, like our sun, will puff up into red giants, then shrink down into white dwarfs, hot, dense remnants that slowly cool over time. After trillions of years, even the smallest, most fuel-efficient red dwarf stars will finally burn out. When the last star goes dark, the universe enters what's called the degenerate era, a cold, dark stretch where only remnants remain. White dwarfs, cooling into black dwarfs, neutron stars, black holes. No new light, no new warmth. Then comes the black hole era, when most ordinary matter is gone and enormous black holes dominate what's left of the universe. They grow by swallowing whatever remains. But even black holes don't last forever. Through an incredibly slow process called Hawking radiation, which we'll get into more in a moment, black holes gradually evaporate, shedding mass one photon at a time, over timescales measured in trillions of trillions of trillions of years. And then, when the last black hole finally evaporates, the universe becomes nothing but a vast, diffuse ocean of scattered fundamental particles. Temperature asymptotically approaching absolute zero. No remaining structure, no temperature gradients left to generate any usable energy. That's heat death. Not an explosion, not a scream, but a final, quiet exhale. The universe drifting into a sleep it never wakes from. But, and this matters, quiet doesn't mean it isn't beautiful. No end, only transformation. There's something that thermodynamics, the science of heat and energy, teaches us. Energy is never created and never destroyed. It only changes form. In a universe that has gone through heat death, when everything has reached perfect equilibrium, there's a concept in quantum physics called quantum fluctuations. Even in the most perfect vacuum, even at temperatures closest to absolute zero, particles can spontaneously pop into existence and vanish again in incredibly brief moments. This isn't speculation. It's been measured. And in a universe that exists long enough, and long enough here means numbers so large that ordinary numerals can't really do them justice, even the rarest quantum fluctuations will eventually happen, including fluctuations large enough to spark a new Big Bang. A universe, what from the fluctuation of a dead universe. A new flame from the ashes of an old one. Not creation from nothing, but rebirth from silence. Our universe, whatever its ultimate fate turns out to be, is right now in the most beautiful phase of its existence. Stars are still burning. Planets are still forming. Life is still finding ways to take hold and flourish in places we never expected. We are living in the springtime of the universe, a brief, brilliant moment in a piece of music that runs longer than any mind can hold. And whether the universe is reborn or not, whether the big bounce happens or not, this moment, tonight, your breath right now, is real. It's happening. It's an indelible part of the history of the universe. Nothing that has happened can be erased. Every moment is etched into the fabric of reality, including this one. Try a small thought experiment. Imagine you're a two-dimensional creature. You have width and height, but no depth. You live on the surface of a vast, flat sheet of paper. You walk forward in a straight line for a day, a year, a century, and never reach an edge. You conclude, this sheet is infinite. But the sheet might actually have been rolled into a sphere, and if you walked far enough, you'd arrive right back where you started, without ever realizing you'd gone all the way around. Our universe, according to some models, might work in a way not entirely unlike that. What shape is the universe? This is one of the biggest and strangest questions science is currently wrestling with. Not what does the universe contain, or how does the universe work, but what the universe actually looks like from the outside. The problem is, we can't look from the outside. We're inside it, and that's the central challenge. Think about an ant crawling on the surface of a balloon. The ant can't see the whole balloon. It only sees the surface directly under its feet. But if it's clever enough, it can draw a triangle on the surface, measure the angles, and notice that they add up to more than 180 degrees, something that doesn't happen on a flat surface. From that, it can deduce that the surface it's standing on is curved. Physicists do essentially the same thing with the universe, except instead of measuring triangle angles, they measure the patterns in the CMB, study how light from distant galaxies gets bent, and compare the universe's actual matter density to a critical threshold called the critical density. Current results suggest that our observable universe is very nearly flat, or more precisely, flat within the margin of measurement error. But nearly flat isn't the same as perfectly flat. And flat, in the cosmological sense, doesn't mean flat like a sheet of paper. It means that ordinary Euclidean geometry holds at large scales. Still, there are three main possibilities that scientists consider. First, a positively curved or closed universe. Curved like the surface of a sphere, but in 3 dimensions. If you traveled in a perfectly straight line long enough, you'd eventually arrive back where you started. The universe would be finite in size, but have no edge, the same way the surface of a ball has no beginning or end. Second, a negatively curved or open universe, curved in the opposite direction, like a saddle. No matter how far you travel in one direction, you never come back. The universe is infinite and keeps expanding forever. Third, a flat universe, where ordinary geometry works perfectly. Parallel lines never meet. Possibly infinite as well. Current data leans toward the third option, flat or very nearly flat. But that doesn't rule out the possibility that the universe has a strange overall shape at scales far beyond what we can observe. Some models suggest the universe might be shaped like a torus, essentially a giant donut, or even more complex topological shapes that everyday language really can't capture. And our observable universe, the bubble of space roughly 93 billion light-years across, from which light has had time to reach us, might be just a small patch of something vastly larger in ways we can't yet begin to picture. But let's step away from the question of overall shape and look at the universe's internal structure. Because what we find there is even more beautiful than anything we dream up. If you could shrink yourself down small enough to see the entire observable universe in a single frame, you wouldn't see galaxies scattered randomly through space. You'd see a web. Scientists call it the cosmic web. Enormous filaments of matter, hundreds of millions of light-years long, connected at nodes where vast galaxy superclusters sit. Between those filaments are enormous voids, stretches of space that are nearly completely empty. The whole structure looks like a vast three-dimensional spider's web, or like soap bubbles stacked on top of each other, or like the nervous system of some creature too large to imagine. And here's what made scientists do a double take the first time they saw the comparison. The cosmic web looks strikingly similar to the structure of the human brain. The cosmic filaments connecting galaxy clusters, and the neural fibers connecting nerve cells. The nodes in the cosmic web where filaments meet, and the synapses where electrical signals jump between neurons. The empty voids between cosmic filaments, and the spaces between neuron clusters. Now, this is a structural resemblance, not a functional one. The universe is not a brain, but the similarity points to something deeper. Certain mathematical and physical laws give rise to complex network structures, and those laws operate at every scale, from billions of light years all the way down to the micrometers inside your skull. The universe and your brain were sculpted by the same mathematical language, just at scales so different it's dizzying. And the cosmic web isn't just aesthetically beautiful. It's a map of cosmic history. Every filament, every node, every void reflects how matter has gathered and shifted over billions of years under the influence of gravity, dark matter, and dark energy. By studying the cosmic web, cosmologists can trace the universe's formation history backward and test their models of what dark matter actually is. Cosmic voids, the great emptiness we might be living in. But if the cosmic web is the bright threads, what lies between them? Cosmic voids. These are enormous regions of space, some hundreds of millions of light years across, where matter density is extremely low. Not completely empty, there are still some scattered galaxies and material, but sparse enough to be nearly nothing compared to the rest of the universe. One of the largest known voids is the Boötes void, a gap roughly 330 million light-years wide, sitting in the direction of the constellation Boötes. If the Milky Way happened to be at the center of the Boötes void, which thankfully it isn't, we wouldn't have known other galaxies existed until the 20th century, because everything would have been too far away to detect with older technology. But here's the more interesting part, and slightly unsettling if you sit with it too long. We might actually be living inside a void right now. Our Milky Way sits in a region called the KBC void, an area where matter density is roughly 20% below the cosmic average, with an estimated diameter of around 2 billion light-years. If that's right, it might actually explain part of the Hubble tension we mentioned earlier, because living in a below-average density region would affect how we measure the universe's expansion rate. We might be looking out at the universe from an unusual vantage point, from inside an emptiness, rather than from one of the dense filaments of the cosmic web. That's not dangerous, nothing to worry about, but it's a reminder of something worth holding on to. Our position in the universe isn't randomly average. We're standing at a specific corner in a specific neighborhood of an enormous cosmic city, and that vantage point colors everything we see. Since the 1970s, astronomers have noticed something strange. The Milky Way, along with dozens of neighboring galaxies, including Andromeda, is moving in a specific direction at roughly 600 kilometers per second. Not because of the universe's expansion. This is a separate, directional motion all its own. Something is pulling us that way. That direction points toward the constellation Centaurus, and when astronomers looked there, they found an enormous supercluster of galaxies now called Laniakea, a Hawaiian name meaning immeasurable heaven. Laniakea contains around 100,000 galaxies, including our own Milky Way, and stretches roughly 520 million light-years across. At the center of Laniakea, the point that all the galaxies in the supercluster are slowly drifting toward, is something called the Great Attractor, a region of enormously concentrated mass equivalent to tens of thousands of galaxies, hidden behind the thick dust of the Milky Way and very difficult to observe directly. We are falling toward the Great Attractor, slowly, unstoppably, but the expansion of the universe is pushing back against that pull, and by current calculations, we'll never actually get there. But the story doesn't stop there. If something is pulling us in one direction, is something pushing us from the opposite direction? It turns out, yes. In 2017, a research team discovered a structure they named the dipole repeller. It's a region of extremely low matter density, a massive cosmic void, sitting in the direction opposite the Great Attractor. And because matter there is so sparse, the gravitational pull from that direction is far weaker than from the surrounding regions, creating an effect that works like a push. It's not a true repulsive force. It's more of an absence of pull. But the practical result is the same. The Milky Way is being drawn toward the Great Attractor and simultaneously nudged away from the dipole repeller, both forces pushing us in the same direction. Einstein predicted that mass curves the space around it, like a heavy ball resting on a stretched sheet of fabric, creating a dip. And if space is curved, then light passing through that region gets bent along with it, not because any force is acting on the light, but because light simply follows the straightest possible path through space that is no longer flat. That prediction was confirmed for the first time in 1919, when astronomers observing a solar eclipse noticed that starlight passing near the sun was deflected by exactly the amount Einstein had calculated. It was one of the most beautiful moments in the history of science, theory, and experiment reaching out and touching each other. But at cosmic scales, the effect becomes genuinely extraordinary. When light from a very distant galaxy passes close to a massive galaxy cluster sitting between it and us, the enormous mass of that cluster curves the surrounding space, and the distant galaxy's light gets bent, stretched, sometimes split into multiple paths. What we end up seeing are several images of the same galaxy at once, sometimes arranged in a perfect ring around the intervening cluster, called an Einstein ring. Light from a single, distant galaxy doesn't just arrive from one direction. It comes from multiple directions simultaneously, each path a copy of the same light source, having traveled different routes through curved space, taking slightly different amounts of time to get here. Sometimes, two copies of the same supernova explosion from a distant galaxy arrive at different moments, because the light took different length paths. We see the same explosion twice, years apart. The universe replays its own moments back to us. And beyond its beauty, gravitational lensing is an enormously powerful scientific tool. By measuring how much light bends, astronomers can calculate the total mass of the object doing the lensing, including the invisible dark matter. Gravitational lensing, in a sense, is how we see the unseeable. Light bends, and in that bending, the universe's secrets come through. If you asked most people what a galaxy is, the first answer that comes to mind would probably be a massive collection of stars. But the universe, as usual, doesn't agree with the simple definition. There are galaxies that exist with almost no stars at all. They're called ultra-diffuse galaxies, and in the most extreme cases, they seem to be made of little more than gas and dark matter. One of the most jaw-dropping examples is Dragonfly 44, a galaxy in the Coma cluster about 330 million light-years away. When astronomers first discovered it in 2016, they measured its mass and found something deeply strange. Dragonfly 44 has roughly the same mass as the Milky Way, but contains only about 1% as many stars. The remaining 99% of that mass is dark matter. Dragonfly 44 is almost a galaxy made of darkness, a massive cosmic structure that exists and holds itself together because of something we cannot see, cannot touch, and cannot measure directly. But it's there. We know it's there because its gravity affects everything around it. On the other hand, there are galaxies that seem to have no dark matter at all. The galaxy NGC 1052-DF2 is one example, another ultra-diffuse galaxy, but this time, measurements show it moves as if the visible matter is all it has. There's no sign of hidden dark matter inside. This has sparked a major debate in the astronomy community. If dark matter is a fundamental component of every galaxy, why are there galaxies without it? Or more precisely, why are there galaxies where dark matter has been stripped away, pulled out, or carried off by gravitational interactions with larger neighboring galaxies? No one has a complete answer. But the existence of these strange galaxies, galaxies without stars, or galaxies without dark matter, reminds us that the universe has more ways of creating diversity than any of our models can predict. Life doesn't exist only in the light. Sometimes, the most fascinating things are hidden in the dark. Andromeda is coming, and it's not as scary as you think. The Andromeda Galaxy, also known as M31 in astronomical catalogs, is the largest galaxy in our local group, a collection of about 50 galaxies clustered together in a small corner of the universe. Andromeda is about 2.5 million light-years away, so distant that its light takes 2.5 million years to reach us. It's the farthest object visible to the naked eye under ideal dark sky conditions, a faint smudge in the constellation Andromeda. But Andromeda isn't standing still. It's moving toward us at about 110 kilometers per second. And in about 4 billion years, the two galaxies will begin to collide. But before you worry, let me explain what that really means. A galaxy, even one containing hundreds of billions of stars, is mostly empty space. The distances between stars are so vast that when two galaxies pass through each other, the chance of two stars directly colliding is extremely small. The stars will pass by one another like two swarms of bees flying through each other, gravitationally chaotic, but with very few actual collisions. In fact, the two galaxies have already begun to touch, not in their central stellar disks, but in their halos, the extended regions of hot gas and dark matter that stretch far beyond the visible stars. Those halos have already started to overlap and interact. Technically, the merger has already begun. We just haven't reached the most dramatic phase yet. In about 4 billion years, the stellar disks will start to intertwine. Gravity from both sides will pull stars out of their familiar orbits, stretching the galaxies into long, distorted arms and strange shapes. Massive clouds of gas will collide and compress, triggering brilliant waves of new star formation. Then the galaxies will pass through each other, separate, and be pulled back together by gravity. They may pass through each other several times, each time a bit more chaotic, each time more intertwined, until they finally merge into a single giant elliptical galaxy. Astronomers have even given this future galaxy a name, Milkomeda, or Milkdromeda, an awkward blend that somehow feels fittingly intimate. And our sun? It will likely still be there, possibly in a completely different orbit within the new galaxy. Earth, if it still exists by then, which is uncertain, since the sun will expand into a red giant long before that, will simply be carried along for the ride, not crushed, not burned up by stellar collisions, just relocated to a new place in a new home. A galactic merger isn't a disaster, it's a transformation. Two separate things becoming something larger, more complex, and in a way, more complete. The universe has done this thousands of times, in thousands of different places. Every large galaxy we see today is the result of countless mergers in the past. Our Milky Way has already swallowed many smaller galaxies throughout its history, and it's still consuming a few dwarf galaxies right now, one star at a time, pulling them into its orbit. We are not victims of the universe. We are the product of countless encounters and mergers that happened long before we existed. Tonight, if the sky is dark enough and you're looking in the right direction, you might see Andromeda, a faint, quiet little smudge of light. Nothing about it suggests chaos. Nothing hints at the collision waiting ahead, just light. 2.5 million years old. That began its journey long before our earliest human ancestors knew to look up at the sky. Now, gently reaching your eyes tonight. Two galaxies are moving toward each other, slowly, unstoppably, like two people who made an appointment billions of years ago and are now, step by step, making their way toward that meeting. And you, lying here, breathing, listening, you are part of that journey. Not an outside observer, but a small passenger being carried along on a voyage longer than any story humanity has ever told. Sleep well. The universe will take care of the rest. There's a question I want you to keep in your mind throughout this part. Not a question about the universe, but a question about you. Right now, as you lie here, breathing, listening, billions of invisible particles are passing through your body, through your skin, your bones, every cell, every atom, and out the other side, leaving no trace, interacting with nothing as if you didn't exist. Not X-rays, not radiation, but dark matter, something that makes up nearly 27% of the entire universe, yet no one has ever touched it, seen it, or felt it. There's a question I want you to hold on to as we continue, not about the universe, but about you. Right now, as you lie here, breathing, listening, billions of invisible particles are passing through your body, through your skin, your bones, every cell, every atom, and out the other side, leaving no trace, interacting with nothing, as if you didn't exist. Not X-rays, not radiation, but dark matter, something that makes up nearly 27% of the universe, yet no one has ever directly touched, seen, or sensed it. And tonight, we're going to step into the most mysterious corners of reality, where matter becomes invisible, where time stretches and bends, and where space itself might be nothing more than a projection from a two-dimensional surface we've never seen. Dark matter, the thing that holds the universe together. The story of dark matter begins with a simple and unsettling observation. Galaxies rotate. The center spins faster. The outer regions spin more slowly. That's what we would expect. Just like planets closer to the sun orbit faster than those farther away. But when astronomers measured the rotation speeds of spiral galaxies in the 1970s, most notably astronomer Vera Rubin and her colleagues, they found something that didn't add up. Stars at the outer edges of galaxies were moving much faster than the visible matter could account for. If only the stars and visible gas were providing the gravity to hold the galaxy together, then at those speeds, the outer stars should have been flung away long ago. The galaxy should have fallen apart. But it didn't. It held together. That means something else must be providing extra gravity, something invisible, that doesn't emit light, doesn't absorb light, but has mass, and therefore exerts gravitational force. We call it dark matter. And it's not just at the edges of galaxies. Dark matter is everywhere. It surrounds galaxies like an invisible halo, far more massive than the visible stars. It forms the backbone of the cosmic web we talked about earlier, structures of dark matter that formed first, with gas and stars gathering later. Without dark matter, galaxies might never have formed the way they did. But what is dark matter? We don't know. We know it isn't ordinary atoms. It's not hidden gas, not lurking black holes, not neutrinos. The most popular candidates are hypothetical particles called WIMPs, weakly interacting massive particles, particles that have mass but interact only through gravity and the weak nuclear force. It sounds theoretically plausible, but after decades of searching with the most sensitive detectors ever built, we still haven't found a single WIMP. And here's the interesting part we mentioned earlier. Some galaxies seem to have no dark matter at all. The galaxy NGC 1052-DF2 is the most striking example. A galaxy that moves as if there's nothing invisible hidden inside it. This doesn't necessarily disprove the existence of dark matter, but it suggests that under certain conditions, dark matter can be separated from ordinary matter, stripped away by gravitational interactions with nearby massive galaxies. Dark matter isn't something permanently bound to a galaxy. It's something that can be taken away. And right now, as you lie here, billions of dark matter particles are flowing through your body every second, passing through your skin, through your heart, through your brain, and out the other side, completely unaware that you exist. You are entirely transparent to them, like mist to light. There's something both strange and humbling about that. Time passes. A second here is a second there. An hour in your bedroom is an hour on a mountaintop, an hour at the bottom of the ocean. It feels so obvious that no one questions it. But Einstein showed that this isn't true. Time doesn't flow at the same rate everywhere. It's affected by two things: speed and gravity. The faster something moves, or the closer it is to a massive object, the more slowly time passes for it compared to something else. This isn't just theory. It's been measured. Ultra-precise atomic clocks placed on airplanes, moving faster and at higher altitudes, return ticking slightly behind clocks on the ground by mere billionths of a second. The GPS system your phone relies on has to account for this effect every single day. If it didn't, your location would drift by about 11 kilometers per day, simply due to the difference in time between satellites and Earth. Einstein's theory of relativity isn't just philosophy. It's practical engineering you're using every day without realizing it. But on a cosmic scale, this effect becomes far more extreme. Near a neutron star, where gravity is so intense that a teaspoon of its material would weigh more than an entire mountain range. Time passes noticeably slower than it does here. If you could stand on the surface of a neutron star for an hour, though you'd be crushed instantly by the gravity, your clock would only tick through perhaps tens of minutes, while someone observing from afar would see a full hour pass. And near a black hole, where gravity reaches its extreme, time almost comes to a standstill relative to a distant observer. If an astronaut were falling into a black hole, from the outside, they would appear to freeze in place, their motion slowing down more and more, their light becoming increasingly redshifted, forever hovering at the edge, never quite crossing the boundary. From the astronaut's own perspective, they fall in normally, feeling nothing unusual at the moment they pass the threshold. The same moment, two completely different experiences. Neither one is more correct. Both are real, just real in different ways, in different frames of reference. Time is not a uniform flow that moves the same way for everything. It's a flexible structure, bent by mass, stretched by motion, and different at every point in space. And now we arrive at what may be the most bold and most beautiful idea in modern theoretical physics. It's possible that our three-dimensional universe doesn't truly exist, not in a philosophical or spiritual sense, but in a serious physical sense. This idea is called the holographic principle. It emerged from the study of black holes and was developed by physicists like Gerard de Hooft and Leonard Susskind in the 1990s. The story begins with a paradox about information. When matter falls into a black hole, where does the information about that matter go? According to quantum mechanics, information cannot be destroyed. But according to general relativity, anything that falls into a black hole disappears from the observable universe. Both theories are correct within their domains, but here they conflict. Stephen Hawking proposed that the information isn't truly lost. It's encoded on the surface of the event horizon, the boundary of the black hole. That two-dimensional surface contains all the information about everything that has fallen inside. And from that idea, physicists ask an even more daring question. If all the information about a three-dimensional object can be encoded on a two-dimensional surface surrounding it, could our entire three-dimensional universe be a projection from a two-dimensional surface at the boundary of the observable universe? Like a hologram, a flat two-dimensional film that, when illuminated, creates a fully three-dimensional image. The reality we experience every day may be a projection of information encoded on a distant two-dimensional surface. This doesn't mean the universe is not real. Tables, stars, your body, they're all real in terms of experience. But depth, the three-dimensional space we perceive, might be the way the universe represents information, not its most fundamental structure. Space itself might be a language, not a thing. And if space is a language, then what are the smallest symbols it's written in? There's a scale called the Planck length, about 1.6 times 10 to the minus 35 meters. That's about 10 to the 20 times smaller than an atom, and another 10 to the power of 20 times smaller than a proton. It's the scale at which both quantum mechanics and general relativity begin to break down, where the two greatest theories in modern physics contradict each other and stop producing meaningful results. Many theoretical physicists suggest that at the Planck scale, space is no longer continuous. It becomes discrete, granular, like a computer screen made up of individual pixels. If that's true, then space can't be divided forever. There is a smallest unit, a cosmic pixel, below which the very idea of distance no longer makes sense. Space isn't a smooth fabric that can be subdivided infinitely, but a discrete network of fundamental units that cannot be broken down any further. Some theories, like loop quantum gravity, build on this idea, describing space and time as networks of quantum nodes and links, rather than the smooth continuum of relativity. If this is correct, then the universe isn't just a hologram, it's a hologram with finite resolution. A vast image painted with the smallest possible brush strokes, and beneath those strokes, there is nothing left to paint. Every carbon atom in your body, in your bones, your blood, every cell breathing right now, once existed inside a star. That star lived, burned for billions of years, and then died in a massive explosion. And in that death, it released the atoms that would one day become you. You're not just looking at the stars, you're made of them. And tonight, let's sit with the stars for a while, not as distant points of light in the sky, but as living things with their own lives, with beginnings and endings, with quiet deaths and brilliant ones, with the slowest and most extraordinary rhythms the universe has ever created. The first stars, light no one had ever seen. Let's go back in time to an era when the universe was still very young, about 100 to 200 million years after the Big Bang. The darkness of the starless universe, the cosmic dark ages, is beginning to lift. Massive clouds of hydrogen and helium gas, formed in the first moments after the Big Bang, are slowly collapsing under their own gravity. Nothing interferes. No metals, no cosmic dust, no heavy elements, because they haven't been created yet. Only hydrogen, helium, and a trace of lithium. And from those pristine clouds, the first stars begin to ignite. We call them population 3 stars, the third generation in astronomy's backward naming system. But in reality, they were the very first stars to ever exist in the universe, and they were unlike any stars we see today. Without metals to help cool the gas clouds, those clouds had to accumulate far more mass before pressure and temperature could trigger nuclear fusion. The result was stars of unimaginable size, some hundreds, even thousands of times more massive than the Sun. And with that mass, they burned with incredible intensity, millions of times brighter than the Sun, emitting powerful ultraviolet and X-ray radiation that lit up the surrounding space in vast ionized bubbles. This moment is what astronomers call the epoch of ionization. The light from those first stars gradually burned away the fog of neutral hydrogen that filled the universe, making it transparent to light, like dawn pushing back the night. But population 3 stars didn't live long. With such enormous mass, they burned through their fuel extremely quickly, just a few million years, instead of billions like the Sun. Then they died in colossal hypernova explosions, far more powerful than typical supernova, scattering the first heavy elements, carbon, oxygen, iron, silicon, into the surrounding space. Those elements became the raw material for the next generation of stars, and the next. And over billions of years and countless generations, those elements were enriched, made more complex, until one cloud became rich enough to form a star like our Sun, with rocky planets around it, and on one of those planets, life. You are the third, fourth, fifth generation of stellar ash. You are the product of billions of years of element formation, a chemical recipe forged in many different stellar furnaces before finally becoming you. We've never actually seen a population 3 star. They're too distant, too faint, after billions of years of cosmic expansion. But the James Webb Space Telescope is looking far enough back that one day it may catch their light, the light of the first stars, the ones that first lit the fire in the universe's primordial darkness. In our Milky Way, there are stars that are unusually old, not just old in the usual sense, old to the point that they're older than the galaxy they currently live in. That might sound like a contradiction. How can a star be older than the galaxy that contains it? The answer lies in the violent history of galaxies, the mergers, the devouring, and the collisions we talked about earlier. The Milky Way, like any large galaxy, built itself by swallowing smaller galaxies over time. When a smaller galaxy is pulled in and dissolved, its stars don't disappear. They continue to exist, but now as residents of a new galaxy, carrying with them the chemical memory of a home that no longer exists. These stars can be identified by their chemical composition, extremely metal poor, because they formed when the universe was still very young and heavy elements were rare. They are living fossils of galaxies that have been consumed, remnants of worlds that no longer exist, quietly orbiting the center of the Milky Way like ghosts of the past. One such star, the Methuselah star, HD 140283, is estimated to be about 13.6 billion years old, nearly as old as the universe itself. It existed when the universe was still in its infancy. It witnessed the formation of the Milky Way from the outside before being drawn in. It has aged through billions of years, as generations of other stars were born and died around it. We often think of a star's death as one of the most dramatic events in the universe, a supernova explosion so bright it can be seen from another galaxy, releasing more energy than the sun will emit over its entire lifetime. But not all stars die that loudly. Some stars die in complete silence. For especially massive stars, dozens of times more massive than the sun, when their cores collapse, gravity can become so overwhelming that nothing can stop it, not even the pressure of a supernova explosion. Instead of exploding and scattering material into space, the entire star collapses inward, directly becoming a black hole within seconds. No explosion, no shockwave, no final burst of light. The star simply disappears. Astronomers call this a failed supernova or direct collapse, and we've actually observed such an event. Or rather, we've observed its disappearance. In 2009, a red supergiant star in the galaxy NGC 6946, named N6946-BH1, suddenly brightened slightly, and then vanished. No supernova, no glowing remnant, just a star that was there, and then wasn't. Where it once stood, there is now darkness. A new black hole, born not from an explosion, but from silence. There's something about that image. A star that burned for millions of years and then simply wasn't there anymore. That evokes a feeling that's hard to name. Not sadness, not quite loss. Something closer to reverence. For a kind of ending so quiet, so complete, it almost feels like a form of dignity. Not every life needs a dramatic ending to have meaning, but not every star is alone in its journey. In fact, more than half of the stars in the Milky Way exist in binary systems, two stars bound together by gravity, orbiting a common center of mass. Sometimes they're separated by millions of kilometers, sometimes so close that their outer atmospheres touch. And when two stars are close enough, something strange and beautiful begins to happen. Imagine a binary system. One normal star and one white dwarf, the dense remnant of a dead star. They orbit each other in a gravitational dance, slow and steady, lasting millions of years. But as the normal star ages and expands into a red giant, its outer atmosphere begins to be pulled toward the white dwarf by gravity. Matter, hot gas, plasma, begins to flow from one star to the other. Not violently, but gently and continuously, like an invisible stream connecting two worlds. Astronomers call this mass transfer. And when simulated on a computer, it looks almost like two dancers spinning and leaning toward each other, one pouring its energy and substance into the other in a dance without end. Sometimes, enough material builds up on the surface of the white dwarf to trigger a thermonuclear explosion called a nova, a sudden bright flare that can be seen from Earth. Then it fades, only to erupt again decades or centuries later, when enough material has accumulated once more. And in special cases, when a white dwarf accumulates enough mass to exceed a critical threshold known as the Chandrasekhar limit, the entire star explodes in a catastrophic Type 1a supernova. An explosion so bright it can temporarily outshine the galaxy that hosts it, leaving behind nothing but an expanding cloud of gas and heavy elements scattered into space. Love, in the universe, sometimes ends in an explosion, but not always. Some binary stars orbit each other for billions of years without violence, just two worlds traveling together, sharing gravity, holding each other in a slow, steady dance longer than any love story humanity has ever written. And when both finally die, when they both become cooling white dwarfs, or neutron stars, or black holes, they can continue orbiting one another, drawing closer over years, centuries, millennia, as they lose energy in the form of gravitational waves, ripples in space-time spreading outward from their dance. Until, after trillions upon trillions of years, they finally touch, merge. And in that moment of union, they send out a gravitational wave signal echoing across the universe, like the final chime of a cosmic temple bell. Are you sure that what you see is real? Not in a philosophical sense, not a question about dreams or psychological illusions, but in a purely physical sense. When light travels from an object to your eyes, does it move in a straight line? Is the object you see really where you think it is? Does what you see truly reflect the reality behind it? In everyday life, the answer is probably yes. But on a cosmic scale, the answer becomes a beautifully uncertain no. The universe, it turns out, is the greatest illusionist that has ever existed. And its tools are not smoke and mirrors, but gravity and light. When Einstein predicted the unbelievable. Let's go back to 1915. Albert Einstein had just completed general relativity, a theory he had struggled with for 10 years, describing gravity not as a force acting at a distance, but as the curvature of space-time itself caused by mass. Within that theory was a bold prediction. Light, when passing near a massive object, would bend, not because a force acts on it, but because the space it travels through is curved, and light simply follows the straightest possible path in a space that is no longer flat. When Einstein published this, many physicists were skeptical. Light bending due to gravity? It sounded strange. Then, in 1919, astronomer Arthur Eddington led an expedition to the island of Principe, off the west coast of Africa, to observe a total solar eclipse. During the brief moments when the moon completely blocked the sun's light, he measured the positions of stars near the sun's edge in the sky and compared them to their true positions when the sun wasn't there. The result? The starlight had shifted exactly as Einstein predicted. No more, no less. The news spread around the world. Einstein became a legend, and physics was changed forever. But that was only the beginning of the story of bent light. Imagine a perfectly aligned setup, a distant light source, a galaxy, or a quasar. Between it and us, a massive galaxy or cluster acting as a lens, and all three, the source, the lens, and the observer, lined up in a perfect straight line. In that case, light from the distant source is bent evenly in all directions around the gravitational lens. And when we look up, we don't see a single point of light. We see a perfect hulk of light surrounding the galaxy in the middle. That is an Einstein ring, first clearly observed in 1988, and since then captured in increasing detail by telescopes like Hubble and JWST. Each ring is a masterpiece of cosmic geometry. Light from a galaxy billions of light years away bent into a perfect circle by the mass of another galaxy in between. But the beauty isn't just in its shape, it's in the hidden information within it. Because how much light bends, how strong or weak the effect is, depends on the mass of the lens. By precisely measuring the shape and brightness of an Einstein ring, astronomers can calculate the total mass of the lensing galaxy, including the invisible dark matter that no telescope can directly observe. An Einstein ring isn't just beautiful, it's a scale for weighing the universe, a tool for measuring the invisible by observing what it does to light. And sometimes the ring isn't perfect, because the mass distribution of the lensing galaxy isn't perfectly symmetrical. The result is that light from the distant source is stretched into luminous arcs wrapping around the intervening galaxy, strange, elegant curves of light that, in images from Hubble, look like abstract paintings created by an artist in love with gravity. Microlensing. When a small planet bends the light of a distant star. But gravitational lensing doesn't only happen with massive galaxies and galaxy clusters. It occurs on every scale, even surprisingly small ones. Here's something remarkable. Even a small planet can bend the light of a distant star. This effect is called microlensing. When a star or planet passes across the line between us and a more distant background star, its gravity temporarily focuses the background star's light toward us, causing that star to suddenly brighten for a few hours to a few days, then return to normal as the object moves on. That brief increase in brightness, the way it rises and falls over time, contains information about the mass and orbit of the object causing the effect. By analyzing that light curve, astronomers can infer the existence of a planet they've never directly seen, simply from how it bends the light of another star passing nearby. This is one of the most important methods for discovering rogue planets, the free-floating worlds we mentioned earlier, drifting through the darkness of the galaxy without a star to orbit. They don't emit light, and they don't reflect any starlight. The only way we know they exist is when they happen to pass between us and a distant background star, leaving a brief signature in that star's light curve. A shadow of a homeless planet imprinted on the light of a distant star, captured by a telescope on Earth for a few days, and then gone forever. That's all we get, and from that, we know it existed. Microlensing is also used to search for dark matter. If dark matter exists in the form of compact objects with enough mass, they too would produce microlensing signals as they pass by. Surveys like OGLE in Poland and the upcoming Roman Space Telescope scan millions of stars looking for these fleeting signals, tiny ripples in starlight carrying the secrets of invisible things drifting through the dark, galaxies hidden behind dust when the universe hides itself. Now, let's talk about another kind of illusion, one not created by gravity, but by dust. The universe is filled with dust, not dust in the everyday sense, but tiny solid particles of carbon, silicon, iron, formed in the atmospheres of aging stars and spread into space by stellar winds or supernova explosions. These grains are microscopic, smaller than the width of a human hair, but when they gather into dense clouds, they can completely block light from passing through. Our Milky Way is a perfect example. If you look toward the center of the galaxy in visible light, you don't see much. not because there's nothing there, but because a thick layer of dust lies between us and the galactic center, absorbing and scattering the light before it reaches our eyes. That's why we use infrared and radio waves to see through the dust and observe the core. But what's truly striking is that this happens on the scale of entire galaxies, not just within our own. There are entire galaxies containing hundreds of billions of stars that are completely invisible in visible light because they are wrapped in dense clouds of dust. These are called dusty star-forming galaxies, and they were especially common in the early universe, when star formation rates were high and large amounts of dust were being produced. For decades, astronomers looked at certain regions of the sky and saw almost nothing, very little, and they concluded those regions were sparse, quiet, uneventful. Then the James Webb Space Telescope, with its powerful infrared vision, looked at those same regions and suddenly revealed dozens of massive galaxies that had been completely invisible before. Galaxies forming stars at furious rates, blazing in infrared light, yet entirely hidden behind their own veil of dust when viewed in visible light. We looked at the sky for decades and thought some regions were empty. It turns out they weren't empty. They were just wearing a cloak. That raises a deeper question. How many things out there are we looking straight at but failing to see? Not because they don't exist, but because we don't yet have the tools to see through what hides them? The universe, as a layered painting light, bends under gravity, forming perfect rings and strange arcs. Invisible planets leave fleeting signatures on the light of distant stars. Entire galaxies hide behind thick clouds of dust. All of this points to the same idea. What we see is not all that exists. Reality has more layers than what our eyes, or even our telescopes, can capture at any given moment. The universe isn't a flat picture you can take in all at once. It's a work of art with infinite depth. Every time you look closer, every time you use a different kind of light, every time you ask a new question, another layer reveals itself, more complex and more beautiful than the last. And every illusion the universe creates, every Einstein ring, every fleeting microlensing signal, every galaxy hidden behind dust is not a deception. It's an invitation to look deeper, to ask more, and to always remember that the night sky you see is only the first page of an endless book. There are truths that science knows with certainty, not because we've directly seen them happen, but because we've measured them carefully enough to know they are happening bit by bit right now. And from what is happening right now, we can see the future, not through prophecy, but through math, through physics, through the patience of science as it listens to the whispers the universe leaves behind in every measurement. The moon is drifting away, centimeter by centimeter. Each year, the moon moves about 8 centimeters farther from Earth. Not much. You can't feel it. No one notices. But it's happening, steadily, continuously, year after year, and it has been for billions of years. The reason is tides. The moon's gravity pulls on Earth's oceans, creating tidal bulges. But because Earth rotates faster than the moon orbits it, those bulges are dragged slightly ahead of the Earth-Moon line. And that offset mass, in turn, pulls the moon forward in its orbit, giving it a tiny boost, pushing it farther away. At the same time, the reaction slows Earth's rotation, A day on Earth is getting longer by about 1.4 milliseconds per century, not noticeable in a human lifetime. But 4 billion years ago, when the moon had just formed from a massive collision between the early Earth and a Mars-sized body, a day on Earth lasted only about 6 hours. And 4 billion years from now, if things continue as they are, the moon will be about 15,000 kilometers farther away than it is today. Not far enough to disappear, but far enough that total solar eclipses, those moments when the moon perfectly covers the sun from our perspective, will no longer happen. The moon will appear too small in the sky to fully block the sun. We are living in a uniquely special window in Earth's history, when the moon and the sun appear almost exactly the same size in the sky, allowing perfect total eclipses. In the past, the moon looked too large. In the future, it will look too small. Only now, in this narrow slice of time, does that remarkable coincidence exist, and we are lucky enough to witness it. When you look up at the night sky, you see stars, thousands, millions, billions, depending on the telescope you use. They seem like they've always been there, and always will be. But in the history of the universe, this era of abundant starlight is the exception, not the rule. The rate of star formation in the universe peaked about 10 billion years ago, when galaxies were younger, gas was plentiful, and new stars were forming far more rapidly than they are today. Since then, star formation has been gradually declining. There's simply not enough cool gas left in galaxies to sustain continuous generations of new stars. But stars are still being born, even now. In giant molecular clouds scattered throughout galaxies, dense regions of gas and dust are slowly collapsing under gravity, heating up, and igniting into new stars. We are living in what astronomers call the stellar era, a period that spans about 100 trillion years from the Big Bang. And we're only about 13.8 billion years in, not even 0.02% of the way through. In that sense, we're living in the springtime of stars, a youthful, vibrant period when the sky is still filled with light, and new stars are still being born in the hidden corners of galaxies. It won't always be like this. Gradually, the gas in galaxies will be used up, locked inside dead stars, or blown away by stellar winds and supernova explosions. Star formation will continue to slow over trillions of years until the last star is born, shines for the final time, and fades. And the sky will never be as bright as it is tonight, when the universe becomes too vast to see itself. The universe is expanding, and not just expanding, it's expanding faster over time, driven by dark energy. And that leads to an inevitable consequence, one that is quietly, beautifully sad. Right now, we can observe galaxies tens of billions of light years away, because their light has had enough time to cross that distance and reach us. But as the universe continues to expand, distant galaxies will move away faster and faster. And at some point, galaxies far enough away will recede from us faster than the speed of light. Not because they're moving through space that fast, but because the space between us and them is expanding so rapidly that their light can never overcome the growing distance. Those galaxies will disappear from our view, not because they no longer exist, but because their light can no longer reach us. In about 150 billion years, most of the galaxies we can currently observe will have vanished beyond our cosmic horizon forever. Any civilizations that still exist at that time, if any, will look up at the sky and see only the galaxies of our local group, merged into Milkomeda, the galaxy formed from the collision of the Milky Way and Andromeda. The rest of the universe will lie permanently out of view, as if it had never existed. Without records from earlier times, those civilizations would have no way of knowing how vast the universe once was. They would look up at an almost empty sky and might conclude that their galaxy is all that exists. We are fortunate to live at a time when the universe is still young enough for light from its most distant regions to reach us, when we can still see the full, grand picture that future generations will never be able to witness. We talked earlier about the heat death of the universe. When all stars burn out, all black holes evaporate and the universe settles into complete cold equilibrium. But the path to that end is longer than any number we can meaningfully write. And along that path are final moments worth pausing to reflect on. The last star in the universe will likely be a red dwarf, the smallest, dimmest, but most efficient kind of star. Such stars can burn for trillions to tens of trillions of years, thousands of times longer than the current age of the universe. They will be the last flickering lights in an ever darker, colder cosmos. And when the final red dwarf finally fades, when there is no longer a single source of nuclear light left anywhere in the universe, the darkness that follows will be beyond anything human language can fully describe. Not the kind of darkness we see tonight, where billions of stars still shine somewhere, but absolute darkness. An endless ocean with no shore, no bottom, not a single photon drifting through it. Only black holes remain, the cooled remnants of white dwarfs, now black dwarfs, and scattered elementary particles drifting in temperatures near absolute zero. The universe does not end with a bang, not with a scream, but with a final breath, long, slow, and so gentle that the line between existence and non-existence begins to blur. And yet, even in that ocean of darkness, quantum physics reminds us that random fluctuations still occur. And given enough time, longer than any number we can name, perhaps a new Big Bang could emerge from that silence. We've traveled far tonight, from the oldest light left over from the Big Bang, through diamond planets and singing stars, through cosmic cycles with no true beginning or end, through galaxy networks stretched like the mind of a god, through silent black holes and beautiful illusions of light, all the way to the dark ocean of the far future. And now, we return here, to you, to this breath. There's one truth I want you to carry into sleep tonight, not as knowledge, but as a feeling. Every carbon atom in your body once lived inside a star. The calcium in your bones was forged in supernova explosions. The iron in your blood was created in the cores of massive stars that died billions of years ago. You are not a being standing outside the universe, looking in. You are the universe, looking back at itself. For 13.8 billion years, the universe had no one to wonder about itself. And then, from the ashes of stars, from chemical reactions on a small blue planet, life appeared. then consciousness, then you. And tonight, you looked up. The universe, through your eyes, saw itself. That is the most extraordinary thing of all that we've shared tonight. May your sleep be as gentle as starlight, and may you carry with you the feeling that the universe is not just above you, but within you. Good night.